Hey, good afternoon, everyone. Welcome to this year's Leigh prize lecture. It's my great pleasure to welcome you to the premier prize lecture that we have in the Yale physics department. And the Leigh prize lecture is named after Leigh, who received his PhD in 1913 from Yale. He was a researcher, teacher, wrote several books, had a distinguished career, was acting chair and director of the Sloan Physics Lab, where you sit here. For many years, we have had a prize lecture in honor of his name. And if you look at the history of lectures that we have had since 1967, there are many distinguished physicists. Several of them actually went on to win Nobel Prizes and other distinguished awards. And today it's my great pleasure to introduce this year's speaker. We have Professor Charles Kane from the University of Pennsylvania. He's the Christopher Brown Distinguished Professor of Physics. And he has a very distinguished career. His prizes are too numerous to list. I will just mention a few. He won the Buckley Prize, the Direct Medal. He won the Lindbergh Award for Distinguished Teaching. He was elected to the National Academies. And in 2015, he also won the Benjamin Franklin Medal. And his research is focused on the theory of quantum electric phenomena. And this week, he is with us for 3 days. You will have the pleasure of hearing 3 talks. Today is the introductory colloquium, and then there will be 2 more specialized talks tomorrow and the day after. Meng Cheng is hosting him, and if you have interest in meeting with Professor Kane and would still like to get on his schedule, please contact me. Today, we will hear a talk on the emergence of topological quantum matter. Please help me in welcoming Professor Charles Kane.
Well, thank you very much. And it's really a pleasure and an honor to be visiting Yale this week. The Leigh lecture, that's quite an honor. And I have many old friends at Yale, and it's a real pleasure to be able to come and visit them. And there are new friends that I'm making as well. So thank you for inviting me. So this is going to be a kind of a feel-good lecture a little bit. So I want to tell you about matter, and matter, is what everything's made out of. And matter can arrange itself in the most ingenious ways. And so my focus for this lecture is going to be mainly about electronic matter. And in order to set the stage for talking about electronic matter, I want to take you back all the way to the very beginning, back to Benjamin Franklin. Okay. So Benjamin Franklin, I have to confess. So I come from the University of Pennsylvania. Okay. And Ben Franklin was the founder of the University of Pennsylvania. So we talk about Ben Franklin a lot. Now for lunch today, I went to was it Ben Franklin College House? Is that what it? And I saw that there was a statue of Ben Franklin sitting on the bench there. But at Penn we had that first. So look, Ben Franklin's a big deal. So he founded the University of Pennsylvania. Of course, he was one of the founding fathers of the United States of America. So he was a statesman. But in addition to that, he was quite a Renaissance man. He was also a scientist. Okay, and as a scientist, what Benjamin Franklin is known for, he's known for doing the first systematic experiments and observations regarding the phenomenon of electricity. Okay, and so you probably heard the story about Ben Franklin going out into a lightning storm and flying a kite, and that was a rather foolish thing to do. but of course, you know, electricity is the stuff that lightning bolts are made out of. It's also the stuff that makes your socks stick together when you take them out of the dryer. So electricity is a rather ubiquitous phenomenon. And Ben Franklin was you know, the first to sort of you know, take seriously and think seriously about making observations. And so what Franklin discovered is that matter has a fundamental attribute called electric charge. Okay, and he realized that electric charge can be positive and it can be negative. And you know, like charges push each other apart, and opposite charges attract each other. Okay. He realized something else. He realized also that electric charge could flow in much the way water flows in a pipe, and that distinguishes two kind of distinct kinds of materials: electrical conductors, which transmit electric charge, and electrical insulators that don't transmit electric charge. And you know, so this is a fundamental, you know, aspect of our physical world. It's very deep and important. But you know, in addition to being a you know, a deep thinker, Benjamin Franklin was also a very practical man. And so he realized that that this new understanding could be incredibly useful. Okay, and so this enabled Ben Franklin to invent, you know, one of the most important technologies of his day, you know, the lightning rod. And of course, the lightning rod is the way you keep your house from burning down in a lightning storm, by having a conductor go around the side to short the you know, lightning bolts around outside your house, so it doesn't burn down. Okay, and so, you know, this to me is sort of the epitome of what is best about science. Okay, so you know, it's deep, it's beautiful, it's profound, but it's also useful. Okay, and so it's this interplay between deep and beautiful and useful that has animated all of the progress that we've made over the past 250 years, understanding what matter is made out of, you know, what the building blocks are, and what it can do. Okay, and what an incredible ride we have been on for the last 250 years. So let's fast forward to the present day, and electronic matter can do the most amazing things. Okay, you know, really, it's like magic, right? We all, you know, have powerful computers in our pockets, and we can push a couple buttons and make any telephone ring on the entire world. You know, it's amazing what electronic matter can do. Okay, and you know, the reason that came about is because of the understanding of matter that developed over the past you know, many years. And so what I'd like to describe to you is that you know, our understanding of electronic matter is actually continuing to evolve. Okay, and I'd like to, in this talk, describe to you some you know, new electronic phases of matter that perhaps will be able to enable new technologies for the coming century. Okay, and so I want to talk about electronic phases of matter, and so that's going to be the topic here. And so I'm going to be talking about phases of matter a lot, and so let me just to you know, relate this to something that's more familiar. Let me talk about, you know, the more familiar phases of matter. You know, and the most familiar phases of matter are maybe the liquid and the solid phases. You know, like water. Okay, and you know, water can be a liquid that can flow, or it can freeze, and it can be a solid that's rigid. And you know, there's something remarkable about this fact, which is that water, you know, liquid water and ice, they're made out of the same building blocks. You know, water molecules, they're all kind of the same. Okay, and you know, so and yet by putting them together, they can have completely different sort of collective behaviors. Okay, and so just knowing the building blocks isn't enough. Okay, knowing what the building blocks can do when you put them together is a equally fundamental part of the story. Okay, so the liquid and solid, those are phases of matter. For electronic materials, the electrical conductor and the electrical insulator are phases of matter. And, you know, so for instance, if you have a copper wire, then, you know, electricity can flow through the copper wire sort of in the same way water flows through a pipe. Okay, but the, you know, rubber that surrounds a wire that you have is a insulator, and electricity cannot flow through that. Okay, and so these are examples of phases of matter, electronic phases of matter. And so I'm going to introduce you to some new electronic phases. But before I do that, I want to sort of step back and think about what matter is made out of. What are the fundamental building blocks of matter? Okay, and you know, for our purposes, and so this is the physics that came into focus at the beginning of the last century. Okay, when we came to understand what the structure of matter is, and you know, for our purposes, you know, and what emerged from that is the idea that matter is composed of fundamental particles. Okay, and for our purposes, the most important fundamental particles are the electron, the proton, and the neutron. And the important thing about an electron is that it has electric charge. Okay, and so an electron has a charge minus E, a proton has a charge plus E, and so the thing is that every electron has exactly the same charge as every other electron. Okay, and so this is and it has exactly equal and opposite to the charge of the proton. Okay, and so the word that we say is that electric charge is quantized. Okay, and so this is one of the most basic fundamental things about matter. So the proton has charge plus E, the electron has charge minus E. Actually, you know, there's a story about this. You know, Benjamin Franklin, he discovered charge. Okay, so he was the one who got to decide which one was the positive and which one was the negative. Okay. Now, of course, in Franklin's time, they didn't know about electrons. Okay, but so he made his choice as to which was the positive and which was the negative, and he made the most unfortunate choice that he could have made, because you know, this is a source of endless confusion for beginning physics students when they learn that an electric current is flowing this way, but the electrons are going this way. Okay. So we can blame that on Benjamin Franklin. But we're stuck with, you know, so he got to decide, and we're sort of stuck with his minus sign. Okay. So in any case, so electrons, protons, and neutrons, they arrange themselves into atoms. Okay, and an atom is sort of like a solar system, a little solar system where the electrons and protons form the nucleus, and the electrons are the protons and neutrons form the nucleus, and the electrons are orbiting around, sort of the same way the planets orbit around the sun. So this is actually a pretty good description of an atom, except it's incomplete for another reason, which is another one of the sort of revolutions in physics that happened at the beginning of the last century, and that's quantum mechanics. Okay, and so quantum mechanics drastically modified the way we think about the behavior of electrons and atoms. Okay, and what quantum mechanics tells us is that in an atom, the electrons occupy discrete quantized energy levels. Okay, so let me tell you what that means. Okay, what that means is that the electrons in an atom, it's like they're snapped into place. Okay, and once they're snapped in, they're stuck, and there's no sort of wiggle room. So it's sort of like, I don't know if you ever played with Legos. You know, with Legos, you snap them together, and once they're snapped together, there's no play. They're sort of stuck. In order to unstick them, you have to pull by a finite amount. Okay, so the electrons and atoms, they're locked in place, and it takes a finite amount of energy, a finite kick, in order to get them to unstick. Okay, and so that's the picture. And the word we say that there's a minimum energy to excite the electron. What we say is that there is a energy gap for exciting an electron in an atom. Okay, so this fact about the quantum mechanics of atoms allows us to understand the most basic electronic phase of matter, okay, which is the electrical insulator, okay? So what an electrical insulator is it's just a bunch of atoms, okay? And each atom has an electron that's snapped in place, and the electrons are snapped in, they're stuck, they're not doing anything, okay? You could say that, the insulating state, it's the most boring state of matter. It's the state where nothing happens, okay? Every electron stays home, okay? But it's a little bit more interesting than that. One thing you can do with a insulator is you can add an extra electron. Actually, before I say that, one thing I want to say is that, matter overwhelmingly wants to be electrically neutral, by which I mean there are just as many electrons as there are protons, okay? And so in this atom, there's no net charge, right? Because every proton is compensated by an electron. And since they have exactly equal and opposite charge, the charge cancels, okay? So this is electrically neutral, but we could add an electron. So here's an electron that I add, okay? And now we have exactly a charge minus because of Benjamin Franklin, okay? So, but here's the thing. You see, this electron has sort of already paid its sort of unsticking price. And so it can move, okay? So it can hop from site to site, okay? So this electron, this added electron can flow. It can conduct electricity, okay? There's something else you could do. In addition to adding an electron, you could take one out. Okay, so if you take one out, then you have a missing electron, which we call a hole. Okay, and the missing electron, it's like you subtracted minus E. So the charge of this missing electron is going to be plus E. Okay, so it has the opposite charge of the electron. Okay, but here's the interesting thing. You see, this hole is kind of like a particle too. Okay, it can move around. So watch. So the neighboring electron can hop over and fill its place, so it's moved over. It can move over again and again. Okay, so this hole it's like a particle. Okay, it can move around. It's just like, sort of just like the electron we added. But you see, the thing that's different here is that the hole wasn't in the original set of building blocks that we started off with. Remember, the building blocks of matter are electrons, protons, and neutrons. Okay, don't confuse the hole with the proton, which has a charge of plus E. Right, the protons aren't moving around. Okay, they're heavy, they're nailed in place. Okay, but the hole can move around like a particle. So the hole is a particle, but it is a emergent particle. It's something that can only exist within this insulating state. Okay, so this is something that's new and sort of on a little bit deeper level. Okay, and so for an insulator, the fundamental excitations of an insulator are charge minus E electrons and charge plus E holes. Now, you might think that if you could add electrons or holes to an insulator to make it so it can conduct electricity, you might think that might be kind of useful. So in fact, a material that it's easy to add electrons and holes to is called a semiconductor. Okay, semiconductors are pretty useful. Like silicon. Silicon is a semiconductor. Silicon's the material that's in all the computer chips in your cell phone. Okay, so this is useful. All right. Now, silicon is more complicated than this sort of cartoon-like picture that I drew for you. Okay, it's not quite this simple. Okay, but it was really one of the greatest triumphs of the quantum theory of matter that that sort of developed over the course of the last century. Was our detailed understanding of materials like silicon. Okay, and so silicon, it's a it's a piece of stuff. It's like a rock. Okay, it has a particular arrangement of atoms. It has a particular crystal structure. Okay, and it also has a particular specific electronic structure. Okay, and so don't worry too much about what all the wiggles on this graph mean. The point I want to get across here is that it's kind of complicated. There are a lot of specific details. Okay, but these are details that we have mastered. Okay, and we are in good control of those details. And because we're in such good control of those details, that's what has enabled us to do all of the magical things that we can do with semiconductor materials. Okay, so this is really the foundation for all of the technology that we've grown accustomed to in this information age. Now, so silicon is more complicated. There are a lot of details to think about. We also have this sort of cartoon-like picture of an insulator that I told you about, and so there's a point that I want to make, which is I'd like to argue to you that there is a sense in which this cartoon-like picture really is right. Okay, because there's one thing I'll say is that even in real silicon, it's still exactly true that the carriers, the fundamental carriers of electricity in silicon are the charged minus E electrons and charged plus E holes. That fact is still true. Even it's true in the cartoon picture I drew. It's true here as well. Okay, so there's some things that this cartoon gets right. Okay, and this getting it right, there's something deep about this, and this leads me to something I sort of feel is like a very deep and beautiful idea in physics. And so the way that I like to say it, I sort of like to say that theoretical physics is kind of like a impressionist painting. So this is a nice painting. It's beautiful. But it's not exactly right. Okay, if you stand up, if you look at it too close, you look at it and you see all the colors, they're not all right. They're all kind of wrong. And it's just these blobs of paint. Okay, it's not an exact representation of reality. Okay, but if you step back from it, it kind of makes you feel a certain way. And there's a sense in which it kind of captures the moment. Okay, it gets that right. Okay, and I'd kind of like to argue to you that these these models that we have in physics, in physics we don't have an exact description of nature. We have these models, these simple models. Maybe they're cartoon-like simple models. Okay, but there is a sense in which those cartoon-like models get things right. Okay, and I'd like to try to say that sort of appreciating the sense in which these models in physics get things right, that this is a kind of an aesthetic experience. Okay, which I want to share with you and try to get you to be as awed by it as I am. Okay, and so in order to explain the sense in which it gets it right, I need to introduce a new concept, which is the concept of topology. Okay, so topology is a deep and beautiful branch of mathematics. And so what topology is concerned with is the study of objects that can be continuously deformed. So I want you to think in your mind about a piece of clay. And clay, you can imagine stretching it and squeezing it and continuously, smoothly changing its shape. Okay, and so what topology is concerned with is asking the question, well, what kinds of shapes can be smoothly distorted into one another? Okay, and So the classic example for thinking about this is to think about the sense in which a donut is the same as a coffee cup. Okay, and so if you have a donut, then you can imagine if it was made out of clay, you can imagine stretching it and squeezing it, changing it just a little bit each time, but then at the end of the day, it's turned into a coffee cup. Okay, of course, the hole in the donut turned into the handle of a coffee cup. So you know, in terms of topology, the donut and the coffee cup are the same. Okay, and so topologists will they like to figure out some way of saying why things are the same. You know, just because, you know, these are it doesn't mean that everything is the same. Okay, things can be different. So for instance, if you have the surface of a sphere, like the surface of this orange, okay, you can continuously deform that shape as well. You can step on it and squeeze it and turn it into a pancake. Okay, but you can't turn it into a donut without poking a hole in it. And that's against the rules because you can't poke a hole smoothly. You have to go from not having the hole to having the hole, and that can't happen smoothly. That's a discontinuous process. Okay, so the sphere and the donut are different, and so topologists like to you know sort of come up with a way of characterizing whether things are the same or different, and so what they do is they introduce what's called a topological invariant. Okay, and in this case for these shapes, it's just counting the number of holes. Okay, and we call it the genus. So a sphere has genus 0 and a donut has genus 1. Okay, and you can imagine fancier donuts that have more holes in them. Okay, and those would be different as well. Okay, so look, so topology is a, you know, it's a beautiful, you know, branch of abstract mathematics. So what does that have to do with, you know, materials, electronic materials, and, you know, so how's that relevant? Okay, and so what I'd like to argue to you is that, you know, this cartoon picture that I had of an electrical insulator, okay, that it's kind of the same as the more complicated description of a real material like silicon, that these are the same in the sense of topology. Okay, in the following way that you can imagine, if you have the real complicated silicon, you know, it has all of its atoms, you know, on this, you know, arranged in its crystal arrangement. In your mind's eye, you can imagine sort of separating the atoms and making them get further and further apart. Okay, and you can do it very slowly and smoothly, so that nothing drastic is happening along the way. And if it stays an insulator the whole time, then by the time you've gotten them very far apart, then you have something that looks like it's a bunch of independent atoms that maybe it looks a lot more like this cartoon picture. Okay, so there's a sense in which these two are really kind of the same. Okay, in the sense of topology. Okay, now of course, you know, this picture is a lot simpler than this one. Okay, so maybe it's nicer to think about it. It's like, you know, for surfaces, you know, the sphere is the simplest surface that doesn't have any holes in it. Okay, and the sphere is very nice. It's very symmetrical and beautiful and pleasing to contemplate. Okay, but that doesn't mean that every surface has to be simple. Okay, surfaces can be much more complicated. So this is Dave the octopus. And Dave the octopus has a more complicated shape. Okay, as long as he keeps his mouth shut, I think his genus is still 0. Okay, so you know, so sometimes when you know things are simpler if you think about the simpler case. Okay, and so you can, by thinking about the sphere, maybe you get some insights that are more general and apply in all cases. Okay, for example, if you know, when you think about it like this. Okay, now what I'll say is that most electrical insulators are kind of the same as a trivial atomic insulator. Okay, so if I think of the trivial atomic insulators basically being like a sphere, then maybe silicon is like Dave the octopus, but it's topologically the same. Okay. But when you say it like this, then you're invited to ask the question, well, could something be different? Okay. So in pictures, is there an analog of the donut? Okay. And the remarkable answer to this question is yes. Okay. And these are fascinating electronic phases of matter that I want to introduce you to. Okay. And I'll just say one other thing that, you know, this quantum theory of matter, this has been around for many decades. And so this is a situation where nobody had thought to ask the question like this. Okay. And if people had thought to ask the question like this, topological insulators would have been discovered much sooner. Okay. But when you do ask the question like this, then you're led down this path of discovery, which leads into amazing places that I'd like to show you. Okay. So I want to tell you about topological insulators. And the way I always like to think about the simplest version of a problem that is simple enough to maybe you can get your head around it. Okay, and the simplest version of a topological insulator is a one-dimensional topological insulator, which is a polymer. So what a polymer is it's just a chain of atoms. Okay, and polyacetylene is a particularly simple polymer. It's a chain of carbon atoms with some hydrogen atoms attached. Okay, and it's a one-dimensional chain. So the thing that's interesting about polyacetylene is that it is an electrical insulator. Okay, but it's an interesting electrical insulator because what polyacetylene wants to do, what it wants to do is it wants to dimerize, by which I mean it wants to alternate between having strong bonds and weak bonds. Okay, so every other atom is closer to one another. So I have a strong bond, weak bond, strong bond, weak bond. Okay, that's the sort of happiest configuration that polyacetylene has. But you see, the thing that's interesting about this is that there are two ways you can do it. Okay, because you can either alternate strong bond, weak bond, strong bond, weak bond, or you can do weak bond, strong bond, weak bond, strong bond. Okay, and so I would like to argue to you that these two configurations of this electrical insulator are topologically different in the sense of topology. Okay, because in order to smoothly go from this one to this one, you'd need to go through an intermediate point where both the bonds are the same. Okay, and that's not an electrical insulator. Okay, so the kind of impressionist picture I want you to have for what's going on here. So I told you that in an insulator, the electrons are kind of snapped into place. Okay, and so in this insulator, what happens is the electrons are snapped into place, but there are twice as many spaces as there are electrons. Okay, so you're sort of snapped in every other one. Well, for now, think of it as infinite. We'll get there. Yeah. Think of it or infinite, or you could imagine it periodic boundary state. So let's not worry about that, Nick. Okay. Yeah. That's right. Yeah. So yeah, fair enough. So but my point here is that in one of the phases I'm occupying the blue wells. Okay. The other phase I'm occupying the red wells. Okay, and they're snapped into place, nothing's happened. Another point I want to make is that, again, matter is overwhelmingly electrically neutral. Okay, and so both of these configurations are electrically neutral. They're just enough electrons to compensate the protons. Okay, so you can ask the question, so what? Okay, and again, Nick, it sort of goes on forever in both directions. Okay, so you can ask the question, why does this matter? Why should we be interested in this? And in order to explain why this matters, I want to show you a magic trick. Okay. So here's my magic trick. Okay. So I'm going to start off with my my polyacetylene. It's in one phase. It's in, I think, the A phase where I'm in the blue wells. Okay, and again, this is electrically neutral. It's an electrical insulator. And I told you that electrical insulators are interesting because you can add electrons to them, and the electrons can flow and turn it into a conductor. Okay, so let's do that. Okay, let's add an electron to our insulator. So there's my extra electron. Okay, so now we have exactly a charge of -E. Okay, so I've added all the charge I'm going to do now. I'm just going to rearrange things a little bit. Okay, so this is my magic trick. Okay, so first I'm going to move these electrons over a little bit. So, oop, there they go. Do it again. Oop. Okay. So, I want to ask you a question. What happened to the original charge that I added? Okay. I know what you're thinking. I know that at least there's some wise guy out there who's going to say, it's right there. Yeah, you're right. But think about it. Okay. Oops. What happened here? Yeah. There's no charge in the middle. Okay, because everything is electrically neutral in the middle. The only place there's any charge is where the electrons are kind of bunched together. Okay, and where the electrons, it's bunched together here and bunched together here. These two places look exactly the same. So exactly half of the electric charge is here, and half of the electric charge is here. Okay, the electron that we added has split in half. That's the magic trick. I just cut an electron in half. I didn't really cut an electron. You can't really, electron is an indivisible particle. You can't do that's impossible to do that. Okay, but somehow we managed to accomplish that here. Okay. And so this is one of the most amazing things I ever learned. So I think this is amazing. I'm not the only person. So John Preskill is a very distinguished theoretical physicist, somebody I deeply admire. Okay, but in addition to being a distinguished theoretical physicist, he moonlights as a poet sometimes. And so when he sees something that he thinks is interesting or something he's inspired by, sometimes he's inspired to write down a poem about this. And so he heard about this or something related to it when he heard a talk by Leon Valence, who's another great physicist that many of us know. Okay, and so Preskill said it like this: you have to admit it's legit. Electrons can split. So there's something interesting going on here. Okay, and so what is it? So let's think about what's going on. So one thing you can see here is that in between, you see on the outside, we had the electrons there, they're occupying the blue wells. We're in the A phase. On the inside between, they're in the other state. They're occupying the red wells. Okay, so this half of an electron, this charge E/2, is existing on the boundary between two different topological phases. Okay, and so this is the essence of what topological electronic phases of matter are about. Okay, so if you get this, then you understand what a topological insulator is. Okay, and so the way I'll say it is that the impossible occurs at the boundary between different topological phases. Okay, so I have a boundary between the A phase and the B phase, and half an electron lives on that boundary. Okay? So somehow having the boundary between two topological phases allows something that otherwise would be impossible to happen. Okay? Now, the point I want to make, this is a very simple kind of cartoon-like example. The thing I want to make is that there are many more examples of this phenomenon. Okay, and I want to introduce you to some of them. And I would like to show you that the impossible things that they allow are remarkable. Okay, and so the first example that I want to give you, it's motivated by a problem, which is a problem with making tiny electrical conductors. The problem is, as you make your electrical conductors smaller and smaller, you have to have electrons flow through them. And the problem is that the flow of electrons in tiny electrical conductors is kind of disorganized. Okay, and this gets worse as you make them smaller. It's kind of like have you ever been in a crowded hallway, and you're trying to get where you're going, you're bumping into people, and it's hard to get where you're going. Okay, so that's how electrons feel. Okay, so wouldn't it be nice if we could do something about this? You might think, how might you go about trying to organize the flow? And we might take a cue with how we try to organize traffic. Okay, to organize traffic, we make a divided highway. Okay, and on a divided highway, the flow is much more organized. And so what I'd like to show you is that a topological phase of matter can precisely accomplish this, okay, and organize the flow of electrons, okay? And this topological phase, it's the mother of all. It's the topological phase that we understood first, and it's the topological phase that we understand the best, okay? And has a name. It's called the quantum Hall state. Okay, it's called the quantum Hall effect. And what I'll say, it's a two-dimensional topological insulator. So by two-dimensional, a piece of paper is two-dimensional, very thin, right? And so if you have an electrical insulator where everything is confined to a two-dimensional plane, or maybe it's confined to the two-dimensional interface between two different materials. Okay, so that's what it means to be two-dimensional. And what the quantum Hall state is it is an electrical insulator, okay? But it is an electrical insulator that is characterized by an integer topological invariant, okay? Sort of like the genus that distinguishes a donut from a sphere, okay? There's an integer topological invariant. Okay, it has a fancy name. It's called a Chern class. Okay, but the important thing about this, though, is that if you have this insulator, then it guarantees that if n is the topological invariant, the integer, then there are n lanes of one-way conductors on each side of the sample. Okay, and so it's precisely like the divided highway. Okay, now these one-way electrical conductors are truly remarkable. Okay, because if you're an electron, and you're in one of these one-way conductors, the only choice you have is to go forward. Okay, there's no other way you can go. Okay, it's like, there are no electrons, there are no cars turning around on the interstate, right? They're all going forward. Okay, it's actually even more remarkable than that. Let's suppose that you could just have one of these one-way edges by itself. Okay, so let's cut the bottom off. So I just have a single one-dimensional system that is this one-dimensional edge state. Let's suppose you had that. Let's think about what you could do with that. So if you had this one-way edge state by itself, you could put the entrance to the edge state inside your refrigerator. and the exit to the, and the other end could be outside your refrigerator. And then you'd have a way of running your refrigerator without having to plug it in, right? Because these one-way conductor would carry heat from the inside of your refrigerator to the outside, and that's what you need. That's what you need that's what a refrigerator is supposed to do. And if you could do that, you'd be rich. Okay, you'd solve all the world's energy problems. Okay, that would be great. Okay, there's just a catch, right? Which is, in addition to violating the no free lunch principle,
Charlie, we got free lunch.
it violates fundamental principles of physics. Okay, it's impossible. You can't do it. Okay, but this impossible thing is possible on the boundary of a topological phase. Okay, so it's the same type of thing that I told you about before. Now, of course, if you have this on the boundary, of course, there has to be another boundary on the other side. Okay, and if you stuck this in your refrigerator, you can't get around having to stick this one in the refrigerator too. Okay, and that's the reason that you're not going to get rich off of this. Okay, but what this topological phase allows is it allows this impossible thing to occur, which is to have this one-way electrical conductor. Now, you might think that having this one-way electrical conductor might be kind of useful. Okay, if you could use it to organize the flow of electrons in your tiny electrical devices. The only problem with that is that in order to get this to go, you need to put this in a strong magnetic field. Okay, so look, actually, I have one more thing I want to say. I want to make the point. I was telling the story a little bit backwards. This phase of matter was not discovered by people sitting by themselves in their room thinking about donuts and coffee cups and things like that. Okay, so this phase of matter was discovered in the laboratory. Okay, and this is and so this is physics of the 1980s. So Klaus von Klitzing, what he was doing at that time is he was doing basic fundamental measurements on the electronic materials that now make up the components of your cell phone. Okay, and what you do if you want to study the basic electronic properties is you measure the electrical conductance in a magnetic field. Okay, and what von Klitzing observed is that the resistance has these very flat steps. Okay, and the value of the resistance on those flat steps is incredibly accurately quantized in units of these fundamental constants. So H is Planck's constant. That's sort of the fundamental constant for quantum mechanics. And E is the electric charge. Okay. So this quantization is so incredibly accurate. Okay. It's basically, this is a number you can measure to 1 part in a billion. Okay. 9 digits of accuracy. Okay. So one way you could think of it is that it defines an integer, 1.0000 with 9 zeros. Okay. Or another way you could say it, if you believe it's an integer, then you can measure this combination of fundamental constants to 9 digits of accuracy. Okay. In fact, this is so good that, actually just in the last couple of years, the ruling authorities for standards and units, the people who keep track of what the definition of the meter and the kilogram is. Okay, so they made the decision that the standard for the kilogram should no longer be the mass of this particular rock that was stored in a vault in France. Okay, literally, there was a piece of stuff. I mean, it was not just a rock. It was a particular piece of stuff that was stored in France that was the kilogram. Okay, but you know, the only problem with that is that standard is only as good as how accurately you can measure the mass of that rock. Okay, and this experiment you can do much more accurately than that. Okay, so the people in charge of the standards made the decision that it is now this experiment which defines the kilogram. Okay, so it's that good. Now, at the time, this was a incredible puzzle. Okay, because you know, so you have this virtually perfect measurement. It's not like the sample was perfect. It's not like you're doing it on a perfect material. So this is a picture. This isn't von Klitzing original sample, but it's a sample from a few years later. And look at it. It's all kind of dirty and globs of solder and dirt. It's all kind of a mess. Okay. So you have this imperfect sample where you have a virtually perfect conductance. How could that be? Okay. And so it was this experiment that inspired sort of some geniuses in theoretical physics, people like, you know, Bob Laughlin, David Thales, and others, to think very deeply about this. Okay, and what emerged from that is the idea of topology. Okay, and the idea that what you are measuring here is you're measuring a topological invariant. And you see, the thing about a topological invariant is you can't screw it up. Okay, so maybe this sample is more like you know, Dave the octopus than a sphere. Okay, but Dave the octopus still has a precisely quantized genus. Okay, and so that's that. Now, what I was gonna say is you know, you might think that if you could have this one-way flow of electrons, you might think that could be kind of useful. Okay. The problem with it is, in order to get this to go, you need a big, strong magnetic field. So notice this is in Tesla. In order to get, you know, several Tesla of magnetic field, you need a big, strong electromagnet. Okay, and you don't want to have to carry that around in your pocket. Okay, and so there's a question whether one can get physics like this to go without having this strong magnetic field. Okay, that's a hard problem. It's a problem that people are continuing to work very hard to try to solve. Okay, and what I want to tell you about is I want to tell you about one approach that you might take. Okay, which uses another topological phase of matter. Okay, which is called a three-dimensional which is called a topological insulator. Okay, and the way that I like to say what that is. So, what a three-dimensional topological insulator, it's sort of like a chocolate treat that is wrapped in tinfoil. Okay, in the sense that you know, the chocolate is it's an insulator on the inside. Okay, but it is an electrical conductor on its surface. Okay, so the tinfoil is like an electrical conductor. The only problem, this analogy isn't quite right though, because if a topological insulator was a chocolate treat, it would be a very frustrating chocolate treat, because if you tried to unwrap it, you would discover that it was still wrapped. Okay, you can't unwrap it. Okay, and the reason for that is because the wrapper, the conductor, this conducting on the surface, is another example of an impossible thing. Okay, the 2D conductor by itself is impossible. Okay, and so that means that you can't peel it off, because if you peeled it off, then you'd have it by itself. Okay, but it also means that if you have it on the surface of a topological insulator, then you can't get rid of it. Okay, it's topologically protected. Okay, and so so this you know, in a sense, this two-dimensional conducting state that is on the surface of a three-dimensional topological insulator, it's kind of it's an impossible 2D conductor that is in a sense half of a regular 2D conductor. We kind of cut that in half. And this 2D conductor has a very specific signature in its electronic structure. Okay, and now I don't want to go into the details of the terminology here, but what we say is that the signature is a single Dirac cone on the surface electronic structure. So there's a very specific property that this surface electrical conductor has. Okay, so now you know, I told you that you know, the quantum Hall effect was discovered first in the lab, and then you know that inspired theoretical physicists to think about it, and then some understanding of topology emerged. So the story of topological insulators is a little bit backwards for that. Topological insulators were actually kind of discovered by pure thought. Okay, and so this is I played a little bit of a role in this, but the idea was just starting off, you know, came with the idea that maybe such a thing was possible. Okay, and then writing down a kind of cartoon-like model in which that one could understand. Okay, so that's what happened first, is this cartoon-like model, kind of almost like the cartoon picture of an insulator that I told you about. Okay, and then, you know, that seemed promising, and so then that motivated us to then try to get more detailed description of more realistic materials, the electronic structure of more realistic materials, and then it became apparent that maybe a material called bismuth selenide would be a material where which should be a topological insulator. Okay, and so we had there was a you know a prediction, and you know, if that's the only thing that happened, this prediction had been made, then this would be kind of an interesting, amusing, you know, side story in physics, but then it would have, you know, not really had much staying power. But what made this turn into something, you know, that was really exciting was the fact that it came to life in the real world. So people were able to grow these materials, okay, and so one has to, you know, be able to learn how to grow. And again, bismuth selenide is it's a piece of stuff. It's like a rock, okay. You can hold it in your hand, so then once you have it, then you need to do an experiment in order to demonstrate that it is what you think it is, okay. And so what people did is they basically took a kind of a fancy picture of bismuth selenide using a technique called angle resolved photoemission spectroscopy. But basically what that's doing is it's taking a fancy picture of the surface of the crystal, which is able to diagnose the specific electronic properties that the surface has. And just, you know, what I'll tell you is that this picture here shows a textbook perfect single Dirac cone, which is exactly what you expect to see on the surface of a topological insulator. Okay, so this discovery sort of kind of unleashed the floodgates, and so there are now many versions of this kind of thing that people can study and do experiments on, and this is a very active field. Okay, in the just remaining time, do I have just a little bit more time? Am I doing okay? Okay, good. So I want to tell you one more version of this story. Okay, one more version of making something impossible happen. Okay, and this final version is also motivated by a problem, and the problem is how can you make a quantum computer? Okay, So this is one of the grand challenges for our century, okay, making a quantum computer. And so just, to get you on board, classical ordinary computer is a device for manipulating classical information. Classical information are just numbers, which can be, you can think of as binary numbers, ones and zeros. Okay, so, like the number 5 in binary looks like 101. And what a simple-minded classical computer is just a device that takes some classical bits, does an operation on them, and then spits out the answer. Like I added 2 to it, and I got 111, which is 7. Okay, so that's what a classical computer does. Now, what quantum mechanics allows, so a quantum computer also manipulates bits, which are ones and zeros. But what quantum mechanics allows is it allows you to have a quantum bit, which can be 1 or 0, or it could be both of them at the same time. Okay? Now, if you haven't studied quantum mechanics before, don't expect to be able to understand this. Okay? Because I don't understand. Okay? And, I do understand quantum mechanics. I mean, I have a PhD. And let me actually, if you have studied quantum mechanics, and you think you understand this, then you should ask yourself whether you really do. Okay. So there's something deep and mysterious about this fact. Okay. But the thing is, it is a fact of nature. Okay, that a quantum bit can be 1, 0, or both at the same time. Now, let's suppose you have several quantum bits. Okay, then if you have n quantum bits, then they could be all 2 to the n of the n-digit binary numbers at the same time. Okay, so here I did it for 8. Okay, and so now a quantum computer, if you could make one, would be a device that takes quantum bits and does an operation and then spits out an answer. Okay, so then you can ask, well, let's suppose I gave it this state, which has all of the numbers in it. Then it spits out all of the answers. Just one shot. Okay. In order for a classical computer to do all of that, you'd have to do it 2 to the n times. Right? Looks pretty good, huh? Okay. If you think it's too good to be true, you're right. It is too good to be true. It's not that good. Okay. But it is still good in that there are classes of problems that a quantum computer can solve much faster than a classical computer. Okay, and so this is a tremendous motivator for us to figure out how to make this device. Okay, problem is it's a hard problem. Okay, and the thing that makes it hard is there's a fundamental problem with quantum mechanics, which is that this combination being both 0 and 1 at the same time is a very fragile situation. Okay, the problem is if you look at it to see which it is, then you don't measure you don't see that it's both of them at the same time. You see it's one or the other. Okay, and which one you get is like flipping a coin, 50% probability. Moreover, after you've measured it, it's definitely what you saw. It's no longer in the combination. Okay, and so what that means is that if you look at a qubit, you kill it. Okay, so the problem is, the practical problem then is, how do you keep a quantum computer from accidentally measuring itself? It doesn't have to be a person that measures it. Okay, and so this is a hard problem. This is the decoherence problem in quantum mechanics. So how do you do this? And so there are a lot of ideas for how you might go about doing this. And here at Yale, there are people are doing trying to precisely solve this kind of problem. Okay, and what I want to tell you about is I want to tell you about an approach which is different from what we're doing. You know, so one thing you might try to do is just make your qubits as isolated from each other as possible. Okay, so I want to tell you about a different approach which takes advantage of another topological quantum state. Okay, and so the idea here is to split the qubit. Okay, so a qubit it's an object that has can exist in two states. Think of it as like an electron spin or some other two-state system. But the thing is it's a localized object that exists someplace in space. Okay, so it doesn't make sense to have half of one. Okay, that's impossible. Okay, but a topological phase called a topological superconductor accomplishes precisely that. Now, I don't have time to tell you what a topological superconductor, topological superconductor is, let alone a superconductor. But I will say that the way we think about it is very similar to the way we think about all the topological phases that I introduced you to. In particular, this simple polyacetylene thing is very similar to this. Okay, and I also say that the idea that such a thing as a topological superconductor was even possible was conceived of one of the people who conceived of that was Nick Reed here at Yale. Okay, so this is a very interesting phase of matter. Okay, and so the point here is that what the topological superconductor allows you to do is take a qubit and split it in half. So half of it is here, and half of it is at the other end. And what I will say is that in order to measure the state of that qubit, whether it's 1 or 0, requires that you have to be able to look at both ends at the same time. Okay, and so if the only thing you're allowed to do is a local measurement where you can just look at one place at a time, and that is a reasonable thing to hope for, then it's impossible to measure the state. Okay, and that means that the quantum information encoded in that qubit is topologically protected. Okay, and so it's really the same idea. This splitting the indivisible is what the idea of a topological qubit is. Okay, so even this is a really hard problem. Okay, there's been progress. I mean, so people have tried to make these one-dimensional superconductors. There's a particular material, indium antimonide, which is a semiconductor which you can turn into a superconductor by putting a superconductor next to it, and people can do experiments, and they measure a peak here, which is exactly what you'd want to see if it was this sort of half a qubit at the end. Okay, the challenge is making sure that the origin of that peak you're seeing is for the interesting reason rather than some less interesting reason. Okay, and this is something where there's been controversy. There's been so this is a very hard problem, which is still not completely resolved. Okay, but I'll say that my approach to this whole thing is that this idea of making a topological qubit, of making a quantum computer, this is a motivator for us to do lots of really interesting science. Okay, and that's where the fun is along the way, is doing the science along the way. Okay, so this is the one proposal for making a topological qubit. Okay, so I'm just about finished. So let me just leave you with one final thought, which is, so with physics, there's sort of two ways you can go in physics. You can ask the question, what are the most fundamental, building blocks of nature? Okay, and what are the most fundamental rules that govern them. Okay, and that's a worthy, a worthy endeavor, but that's not the whole story. Okay, because once you're given the fundamental building blocks and the fundamental rules, you can ask the question, how does matter that obeys those rules behave? Okay, and that's a bigger question. Okay, so let me give you an example of this, and this is basically sort of classical mechanics. Okay, Newton. Okay, so Newton, discovered his laws of classical mechanics in the 17th century. He wrote the Principia, and in a very real sense, he nailed it. Right, those laws have everything in classical mechanics follows from those laws. Okay, but knowing the laws, Newton's laws, is one thing, but asking the question, how does matter that obeys Newton's laws behave? That's a much bigger question. Okay, and in order to think about that, you need organizing principles for how to think about it. And just as an example, it was hundreds of years after Newton that the concept of energy was introduced. Okay, and energy is an organizing principle for how we think about matter that obeys Newton's laws. Okay, and a very powerful organizing principle. So now it's it's a foundation for physics and all branches of science and humanity. Right, and so what I'd like to say is that quantum mechanics is in a kind of similar situation. Okay, the fundamental rules of quantum mechanics are known. They were laid out in the beginning of the last century. They're still right in the same sense that Newton is right. Okay, but organizing principles for understanding how matter that obeys the laws of quantum mechanics behaves are still emerging. Okay, organizing principles like topology, okay, and other things. Okay, and so this makes it a really exciting time to be a physicist. Okay, because there are lots of new ideas that are coming, and there's lots of new technologies, and a glorious interplay between experiments and theoretical ideas, because matter can arrange itself in the most ingenious ways. So thank you very much.
We have time for some questions, but we should use the mic so that long room can hear us. Any questions? Is this on? Can you hear me? Oh, okay. My question is about the polyacetylene and the fractional charge stuff. I noticed that you drew the polyacetylene molecule with roughly the same spacing as the undulating figure. Would you mind going to that slide, Professor? Yeah, this one. I guess my question is, each of those double bonds has 2 pi electrons, but there's only one dot per tub here. So I guess there's something complicated hidden, and you didn't have time to explain it to us.
So there are 2 extra electrons instead of just 1? Is that the question that you're worrying about? So there is. I did give a little sleight of hand, and so am I answering the right question? That so why is it there's just 1 electron in each space instead of 2? Is that?
Well, yeah, that's a similar question.
Okay.
Yeah.
So let me try to answer. So let me go back further. Okay, so in this picture where I had one electron in every other well, that is actually not quite right. Okay, so so in fact there are two electrons in every other well because electrons have another attribute called spin, so they can be upspin and downspin. Okay, and those and so that means that this charge E over 2 that I have, actually it's going to be charge E over 2 times 2, which is charge E. Okay, but it is still a non-trivial thing because now I have this charge E that doesn't have any spin. Okay, and so that's the real thing that happens in polyacetylene, is that in polyacetylene we have this topological state. The impossible thing that happens on this domain wall in polyacetylene is that you can have a charge without spin, or you can have a spin without charge. Okay, and I opted for not making that complication come up in my description. So so hopefully that's the question you asked. I'm not 100% sure, but yeah.
Very good. Any other questions? Anyone online? Cedric, do you just want to speak up and we'll repeat?
I have topologies, and I don't know, you have like kind of intuitive pictures for why if I were to like squeeze something to a very, very thin layer, and then it's like 1 attom thick or something, and I break it. That doesn't seem like a crazy change to me, but I guess we're talking about something.
Well, no, but there's something. I mean, so look, so if you're talking about it made out of atoms, then you're looking at it too finely. So we have to have something which is smooth. Okay, and there when you split it in two, something drastic changes, which is you go from having just one piece to having two pieces. Okay, and so that number, which goes from 1 to 2, that has to change. That number changes by 1. It doesn't change by a small amount. It goes from 1 to 2, and 2 and 1 are very different from each other. Okay, so that's the sense in which a topological invariant can't change under a smooth deformation. Okay, and now that doesn't mean that you can't go through a transition where a topological where some topological number changes, but you see that there's something special is happening when it's breaking apart. Okay, and so in the context of what we're talking about here, if you went from one phase to the other, what I would say is that you would go through a topological quantum phase transition. Okay, and so that critical point where this topological invariant change, that's a very interesting point to think about. Okay, and so that, you know, and so that's part of the story of topological phases, is understanding the nature of the topological phase transitions that occur between them.
Speaking more about your like this thing where you can't like break it and have the same thing continue afterwards. It has to all exist together with the shell.
Yeah, I think that's right. Yeah, yeah.
Very good. Any last question? Yes.
Sorry about this. So let me talk about like the edge at the two different topological phase, quantum phases. Would it be possible to have an edge that's at like more than 2 quantum phases?
So are you saying, for instance, could I have some place where 3 phases meet?
Yes.
Okay, maybe on an edge. So maybe in 3 dimensions,
Yes.
you could imagine 1, 2, 3 regions that meet. Yeah, maybe one could have something like that. Yeah, yeah, that could be interesting. Yeah, very good point.
Okay. One more.
So in all the examples that you've given here,
like topological properties of the material become like evidence or manifest at some like area or boundary? Is there like a fundamental reason why this is the case?
Well, yeah, I mean, so that's not the only place where these topological things could be invariant. So, but the boundaries are a particularly accessible place where you can access the consequences of the topology. Another example of a way of testing it without a boundary, if you, for instance, if you have a two-dimensional superconductor, if you have a vortex, which is a quantum of magnetic flux, which pierces the superconductors. And so then that doesn't give you a boundary. It gives you a sort of a point-like defect, okay? And the topological nature of a topological superconductor manifests itself on that vortex, okay? So that's an example that's not coming from the domain wall, okay? But in general, to get these protected modes, you need some sort of topological object in real space, okay? Whether it's an interface between two things or some point defect or something like that. And so that's generally where these protected modes show up.
So before we wrap up, I just wanted to ask if you wanted to give a teaser for your other talks tomorrow and Wednesday.
Sure, yeah. So I'm giving a talk tomorrow, which is actually going to be rather similar to this talk, but at a level which is a couple steps higher. Okay, and so I tried to pitch this talk so that it would be accessible to somebody who doesn't know very much physics. You know, the talk next time I hope should be accessible to the graduate students and so it'll be a sort of colloquium level talk where I'm going to talk about similar material, but at a higher level. The talk on Thursday is going to be different. It's going to be about a completely different application of topology, not to insulators, but to metals. Okay, and it turns out the Fermi surface of a metal has a topology. Okay, and I've recently been exploring the various consequences of that fact. Okay, so that's the plan.
Thanks so much.